Right now, tech companies are pouring hundreds of billions of dollars into massive data centers to train large language models. But the man who co-invented the foundational architecture of modern deep learning, a Turing Award winner named Yann LeCun, thinks this entire industry is racing toward a dead end. He points out that despite their ability to write code or generate poetry, large language models are structurally limited. They are autoregressive engines built to do exactly one thing: predict the next token of text in a sequence. This conviction led LeCun to step away from his role guiding Meta's core language model strategy, choosing instead to chase a radically different approach to artificial intelligence. He argues that memorizing human language is a cheap trick. It is completely disconnected from understanding the actual mechanics of physical reality. We have software that can score in the 90th percentile on the uniform bar exam, yet we struggle to build a robot that can reliably fold a t-shirt. Text-based systems lack physical intuition. They don't possess a working concept of gravity, object permanence, or basic cause and effect. To solve this sensory gap, LeCun launched a Paris-based startup called Amy Labs, armed with over $1 billion in seed funding. Their objective is to construct a world model, a system that learns the rules of physics directly by observing raw, multimodal sensory data from the environment. If we want machines to operate autonomously, we have to stop feeding them digital encyclopedias and force them to actually simulate the physical world. Up to this point, the standard method for training an AI on visual data has relied on generative or reconstruction-based models. The mechanical flaw in these systems is their objective. They are trained to predict and recreate every exact pixel of a future frame. The physical world is full of chaotic, irrelevant details. If the camera looks at a forest, predicting the exact movement of every individual leaf consumes an enormous amount of computational power. This obsession with pixel-level accuracy creates fragile systems. They waste processing capacity trying to model background noise instead of understanding the primary action. Biological brains don't work this way. An animal navigating a forest doesn't perfectly reconstruct every leaf. It abstracts the environment to focus strictly on what matters for survival. To replicate this biological efficiency, LeCun developed a technical framework called the Joint Embedding Predictive Architecture, or JEPA. Instead of processing raw pixel data, JEPA operates entirely in representation space. It compresses visual information down to basic structural elements. By stripping away surface textures, the model dedicates its computational power to tracking object trajectory. But the physical world is uncertain. If an object approaches an intersection, it might turn left or right. A traditional model averages those two paths, resulting in a mathematical failure. But JEPA solves this using a latent variable, a mathematical wildcard, allowing the architecture to imagine multiple, distinct future states without breaking its internal logic. This mechanism elevates the AI. It stops being a passive observer guessing the next pixel and becomes an active, strategic planner, capable of anticipating the consequences of physical actions. These mechanics are built to serve a specific goal: artificial general intelligence. But in both industry and academia, the term AGI lacks a stable scientific definition. Using human intelligence as a baseline is also a trap. Humans are highly specialized creatures, evolved for social reasoning and survival, but incapable of high-speed calculus or perceiving 100 dimensions. Researchers at GSFC University and Meta argue that because human ability is actually narrow, AI goals should focus on superhuman adaptable intelligence, or SAI. Progress is measured by the Eta rate metric, a formula that calculates the percentage of human-level performance recovered divided by the computational cost of learning a new task. World models are the specific tools required to minimize this training cost. By learning in representation space, a system can master the physics of a new environment through internal simulation rather than thousands of expensive real-world trials. Building systems that physically act in our world requires a shift from text-based prediction toward models that understand the laws of reality.